So if you're a chemical engineering student, you're going to need some quick ways to estimate heat flow, right? I mean, for everything from a kitchen pressure cooker to a massive industrial heat exchanger. Well, this source gives you those essential tools. Let's jump into the 3 key ideas you really need to get. First up, we've got simplified relations for water boiling on submerged surfaces. To quickly estimate the heat transfer coefficient, you really just focus on one key thing: the temperature difference. That's the gap between the hot surface and the water's boiling point. But, the formula you use actually changes depending on the heat flux and whether that surface is horizontal or vertical. Second, you have to remember that pressure completely changes how boiling works. If you're at a higher pressure, you need to adjust your atmospheric coefficient using a specific correction factor. And, crucially, if you have water that's actually flowing while it's boiling inside a pipe, that's a whole different story. You'll need a separate calculation that factors in both the pressure and that temperature difference. And finally, let's talk about the heat pipe. This device is just brilliant. It's a sealed vessel that uses phase change to move heat with extreme efficiency. So, liquid vaporizes at the hot end, moves as vapor, condenses at the cool end, and a wick pulls the liquid back to the start. The payoff is staggering. This pipe can transfer over 10 times the heat of a solid copper bar. Let's dive into more detail.
You ever find yourself just staring at a pot of water on the stove? Watching those bubbles form? It seems so simple, right? Well, it turns out that underneath that surface, there's some seriously powerful engineering at play. Today, we're going to pull back the curtain and decode the hidden formulas that engineers use to predict and control boiling. We're diving deep into something called phase change heat transfer, which is really just a fancy way of saying we're moving massive amounts of energy by turning a liquid into a gas. So what is actually going on in there? I mean, it's not just about hitting 100 degrees Celsius or 212 Fahrenheit. What's really happening is this incredible high-speed flood of energy moving from the bottom of the pan into the water. And for an engineer, being able to calculate that energy flow with precision, well, that's everything. It's literally the key to designing everything from the pressure cooker in your kitchen to a massive nuclear power plant.
All right, let's get into it. Here's the game plan for our journey today. First, we're going to move beyond just watching the bubbles and get into the numbers. Then we'll tackle a real-world problem, the kitchen pan. After that, we'll see what happens when you crank up the pressure. From there, we'll level up and look at boiling inside an industrial pipe. And we'll finish up by looking at this incredible piece of technology called a heat pipe, and wrap it all up with why this stuff matters so much.
You see, for an engineer, boiling isn't just a bunch of pretty bubbles. It's a number. It's a very specific amount of energy moving from point A to point B. And if you want to control it, you have to be able to calculate it. That's where formulas come in. Think of them as super reliable shortcuts, right? They're basically rules of thumb that have been developed from tons and tons of experiments, and they let us predict exactly how much heat is moving.
So let's start with a scene we all know, a pot of water boiling on a stove. We'll say it's at sea level, so standard atmospheric pressure. In engineering terms, this is called pool boiling on a horizontal surface. It's the most basic case, but it's the perfect place to start. And lucky for us, there's a really neat, straightforward formula we can use. And there it is. Now, I know it looks super simple, but this little equation is our key. Now, to be clear, this is a very specific tool. It's really just for water boiling on a flat surface at sea level pressure, but it perfectly demonstrates the relationship we need to get our heads around. So let's break down what each piece really means.
Okay, first up is H. This is the heat transfer coefficient, and it's what we're trying to find. The best way to think about H is as an efficiency score for how well the heat is moving. A really high H value means you're just incredibly good at getting heat from the pan into the water. Its units, watts per square meter degrees Celsius, tell you how many watts of energy you can push through 1 square meter of the pan for every single degree of temperature difference you have.
Next up, we have the real engine driving this whole show, delta T sub X. This is the excess temperature. And this is the critical part. It's not the temperature of the water itself. It's the difference between the temperature of the pan surface and the water's actual boiling point. This is the big aha moment. For boiling to really get going, the pan has to be hotter than 100 degrees Celsius. That tiny little temperature difference is what unleashes this huge flood of energy.
So let's actually use it. Let's say our pan's surface is just 8 degrees Celsius hotter than the boiling water next to it. That means our delta Tx is 8. Now, watch what happens when we plug that into the formula. We're not just multiplying by 8, we're multiplying by 8 cubed. That's 8 times 8 times 8, which is 512. So that small 8-degree difference gets amplified like crazy, giving us a heat transfer coefficient H of 2,847. Now, to get the actual energy flow, which we call heat flux, we just multiply that powerful H value by our original 8 degrees.
And what do we get? Almost 23,000 watts for every square meter. That's 22.8 kilowatts. To give you some perspective, that's like taking more than 20 standard kitchen microwaves and pointing them all at a single 1 meter by 1 meter spot on the bottom of that pan. It is a massive amount of energy, and it's all being driven by that tiny 8-degree temperature difference.
Okay, but what if we're not at sea level? Or what if we seal the lid on that pot and turn it into a pressure cooker? Well, all of a sudden, the boiling point itself changes, and so does the efficiency of the heat transfer. Our nice, simple formula just isn't quite enough anymore. So how do engineers adjust for pressure?
We use this. This is our pressure correction formula. It's what's known as an empirical relation, which means it's based on experimental data. And it lets us take the heat transfer coefficient we already found at normal atmospheric pressure and just tweak it for a new pressure. It's a fantastic tool that lets us adapt a calculation without having to start all over from scratch. Here's the breakdown. HP is the new, more powerful coefficient that we want to find at our new pressure, which we'll call P. We start with H1, which is the coefficient we already calculated at our starting pressure, P1. The rest of it, that fraction raised to the 0.4 power, that's basically our correction factor. We're calculating exactly how much that pressure change is going to boost our heat transfer. So what does this actually look like? Well, let's take our pan and turn it into a pressure cooker running at 0.17 megapascals. When we run the numbers through our new formula, the heat flux just jumps from 22.8 up to 28 kilowatts per square meter. That is a 23% increase in heating power just from cranking up the pressure. And that is exactly why pressure cookers can cook your food so much faster.
Okay, so we've got a pretty good handle on boiling in a static pot of water. But in the industrial world, think power plants, chemical reactors, you're usually dealing with something way more dynamic. A fluid that's boiling while it's flowing through a pipe. This is called forced convection boiling. And yep, you guessed it, it needs a totally different formula.
All right, I know this one looks a little more intimidating, but the core ideas are exactly the same. This formula is specifically for water boiling as it flows up through a vertical pipe. Notice we still have our friend the delta Tx cubed term. That excess temperature is still a massive driver of what's happening. But look over at the pressure term. It's not just a simple multiplier anymore. Now it's up in the exponent of E, and that tells us something absolutely critical. In flow boiling, pressure has an exponential effect on heat transfer. A little increase in pressure gives you a much, much bigger boost in heating power.
Let's just quickly run through an example. Imagine water at 5 atmospheres of pressure, flowing through a pipe that's 10 degrees hotter than the water's boiling point at that pressure. Okay, first things first, we do the single most important check for any engineer. Get the units right. The formula needs pressure in megapascals, so we convert our 5 atmospheres. Then, we can plug everything in to find H, and from there, it's a simple step to calculate the total heat being pumped into the water over a 1 meter length of that pipe.
And we get a result of 2,810 watts. That's over 2.8 kilowatts of energy being crammed into the water in just a single meter of pipe. Now you can start to imagine how this scales up in a real industrial plant with hundreds of meters of this tubing. Mastering these kinds of calculations is what lets engineers design these massive, super efficient heat exchangers.
So, we've seen how to calculate boiling heat transfer. Now let's look at a device that takes these principles and uses them in one of the most elegant and powerful ways I've ever seen. It's called a heat pipe. And honestly, it's a device that's so efficient it almost feels like magic. But I promise you, it's pure thermodynamics at work.
The concept is just genius in its simplicity. It's just a sealed tube with a special material inside called a wick and a little bit of a working fluid, like water. You add heat to one end, and it vaporizes the fluid. That vapor rushes down to the cold end, where it condenses back into a liquid and releases a huge amount of stored heat. Then capillary action in the wick sucks the liquid back to the hot end, and the whole cycle starts over again. It is a completely passive, self-contained little heat engine.
And this chart, this just shows you how ridiculously effective that simple cycle is. On the left, you've got a solid rod of copper, one of the best materials we know of for conducting heat. It's moving about 0.047 kilowatts of energy per square centimeter, which, is not bad. But then, look at the water heat pipe. It's moving 0.67. I mean, it's not even in the same ballpark. The difference is just staggering.
Let's just put that in plain English. The heat pipe, using nothing but the physics of boiling and condensation we've been talking about, can move more than 10 times the heat of a solid piece of copper.
That right there is the raw power of phase change heat transfer. So we've gone all the way from a simple kitchen pan to a super high-tech heat pipe. What are the big ideas we should be taking away from all of this? What's the real core lesson that's been hiding inside all these formulas and examples?
So here's the bottom line. First, we've seen that we can actually predict this really complex process using some pretty clever simplified formulas. Second, we've learned that we have to be really careful to adapt those formulas for different conditions, like pressure and flow. And we've seen that understanding this stuff allows for incredible technologies like heat pipes. But if there's one single thing to remember, it's this. Moving heat by turning a liquid into a gas is orders of magnitude more powerful than just letting that heat creep through a solid material. It's the difference between a garden hose and a fire hose.
And that really leaves us with a final thought to chew on. We've seen how a simple, passive tube with just a bit of water and a wick can completely dominate one of the best metal conductors we have. So it kind of makes you wonder, where else are these fundamental principles of boiling and condensation being used to quietly revolutionize the world all around us, from cooling the phone in your pocket to powering entire cities?